to participate in this workshop on asymptotics beyond all orders, right? So I had to scratch my head thinking what if anything I could offer on the topic. And this explains a bit of eclectic talks. I think I detected possibly one, maybe two topics where I was involved, into which I was involved and which may hit the business of exponential asymptotics. And it's one kind of bigger. It's kind of roughly the proportion of talks. I will mostly talk about this big problem, which comes from diffraction, and this is those who have worked in diffraction or high-frequency scattering, which is more or less the same, will know that this is one of notorious problems which resisted various attempts to crack it from all possible directions. People tried this and that. They tried everything, including, I think, exponential asymptotics. Then I realized maybe, whether knowing it or not, I was one of those who started my research career a long time ago. It's actually, when I was a PhD student, it was part of my nearly failed PhD, right? For the reason that my supervisor, Valery Smyshlyaev, gave me this product. Try it out of fun. I tried this and that. Nothing worked. Didn't much help to my self-esteem. But as a little consolation, how many years? 36 years later, the fact that it is still largely an open problem, right? Comes as a little consolation. And that this is what did I say? Yeah, one philosophical point that this is arguably as important and canonical PDE as the Airy ODE is, right? Everyone knows that Airy function is kind of simple but very important, canonical, fundamental for connecting two worlds, oscillatory and exponential decay, and light and shadow, right? And on the same token, one could argue that this is, in a sense, next in the hierarchy. This is a PDE rather than an ODE, and it connects not oscillations to decays, but asymptotically modal and asymptotically scattered patterns. And you can say the same thing in different language. In more mathematical or spectral theory, asymptotically discrete spectrum to asymptotically spectral behavior to asymptotically continuous spectrum behavior and transition between the two, right? It is known how to do transition for area, right? If you're an undergraduate student and you have learned basic operations with the ODEs, you need to make a step up, right? To learn a stationary phase method or steepest descent and to connect the two asymptotic regimes, right? If you go to postgraduate study, then you have learned, it depends on your university, I suppose, master level, you know, separation of variables, you know, PDEs, and it similarly doesn't work, but there is no, so far, substitute to this kind of steepest descent method. Maybe exponential asymptotics could not be, who knows? The question remains, and this is, you see, that's kind of my first publication ever, and this is my last publication so far, right? Hopefully not ever, couldn't be sure. Here is the gap, right? Did some easier problems in between. This remains open, but that was the occasion, in fact, with with my colleague Ilya Kamotsky, in a special issue in honor of Valery Babbage on occasion of his 90th birthday, right? We felt obliged to just review this notorious problem and to then make a little further step forward. And then on this, another possible fit to the topic of the workshop, I'll briefly mention in the very end, is in homogenization, when it's actually brother, right? You see a different first letter, Vladimir Kamotsky and Ilya Kamotsky. So Ilya is my current colleague, now full professor in UCL. Vladimir is now somewhere in financial industry, used to be a postdoc with me some years ago. And we did out of fun a calculation when this, in homogenization you can do optimal truncation and have some exponentially accurate error bounds. Right, so here is turning to this first big notorious problem. So it started actually from late 70s, right? So it's good translation, 76, first paper in Russian, so 46 years by now, right? And here is in my first publication in red, which is, I think, directly or indirectly, as I will try convincing you, it has some exponential asymptotic ideas hidden behind it. But then there were some other attempts from, including myself, the second publication from different non-exponential directions, and one more, and a lot of other authors here, more mathematical, some are more engineering type, and then there are more recent activity, some kind of incomplete list of references, some resurgence of interest. So resurgence is another keyword, right, in exponential asymptotics, I understand. Resurgence of interest in recent years, and including a couple of papers with John Ockenden and Dave Hewitt a couple years ago, and this paper with Ilya Komatsky in the special issue in honor of Vasily Babbage. So it's all available in public domain for those interested. Now, so it is a whispering gallery of waves, a diffraction by inflection. What is the whispering gallery? This is the first time I learned that time in Russia, then Soviet Union many years ago, that somewhere in a faraway London, now I'm honored to be working in London, who knew by then, there is the St. Paul Cathedral, and there is this whispering gallery, right, in the St. Paul Cathedral, and then if this is the whispering gallery effect, right? Everyone whoever travels to London, next occasion, go to St. Paul and do this experiment with your friend, right? If one guy whispers right along the wall, and the talker and the receiver, yeah.
We have that in the model.
Right. Oh, okay. Have you tried? Yeah. Does it work? Right. I should try to experiment with two theoretical guys. I should try and do experiment after all. so anyway, this is an intuitive idea, right? That if you are here and whisper, and then the kind of the wave, acoustic wave in this case, right, wants to travel along the ray straight line, but then those rays which make a small angle with the boundary, they reflect the fact that the boundary is curved is crucial, right, important. That's why you need to curved wall. And then there is some enhancement of signal there, right? There is a kind of, or if you start translating it into more mathematical language, bit by bit, then you should have some solutions which are asymptotically concentrated in a boundary layer, right? Near the boundary, right? So that's all pretty well understood from all possible directions, and as long as you have a curved boundary, concave, right? Let's call it, if you look from the direction of the wave field, concave part of the boundary, then what? Then you need to look at, in simplest model for acoustics, it is a Helmholtz equation, and you need an appropriate boundary condition. Let it be Dirichlet boundary condition. And then it is actually an asymptotic regime. It is a high-frequency asymptotic regime, right? Your wave number k has the same dimension as the curvature, right, inverse length. And the wave number is much bigger than the curvature, or it is the same as to say that the frequency is large, right? Frequency is a large parameter, hence it is a high-frequency regime. And then people know that's not a difficult calculation, essentially basics of the boundary layer method, right? If you need to resort to rewrite your Helmholtz equation in curvilinear coordinates, suggested by the boundary is simply S is the arc length along the boundary, and N is the distance, right, to the boundaries. Therefore, the boundary itself is simply N equals 0. And Dirichlet case acoustically soft, right? Could be Neumann. Could be mixed. And as long as the curvature is positive, then you do what is a stretched coordinate, right? You introduce n capital stretched normal variable, and it is again dimensional analysis, natural stretching, because k is a large parameter now, k to the power 2/3, right? Then you balance main order terms in a Helmholtz equation. They're written in these curvilinear coordinates. There will be like 2 or 3 terms, and this suggests this choice of the stretching. And then essentially you have an area ODE, right? And then some kind of, there's some detail actually. This is, you need to take out the oscillatory factor, right? There's kind of along this kind of natural choice. The solution keeps oscillating along the boundary and changes rapidly across the boundary, right? Rapid changes are counted by this stretching. There is this additional so less oscillatory thing, right? It oscillates with the power 1/3 rather than 1. Has a name attributed to Friedlander-Keller, right? Friedlander-Keller asymptotics. And then there is this Airy function with a shift, right? This parameter nu. It's essentially that's separation of variable, right? In underlying, so Helmholtz is asymptotically separable, you could say, right? In this case, and Airy is the ODE. Everyone knows what Airy is for the boundary condition. You need to take some discrete set. You need to take this new separation parameter to be one of the roots, one of the zeros of Airy function, right? And that's it. This all, by the way, this all breaks up as long as all works for as long as curvature stays positive, right? Curvature kappa, right? But if curvature starts degenerating, or God forbid changing sign, everything breaks up. So for the change of sign of the curvature, of course, this is if this is a whispering gallery wave goes from that direction, everything breaks up. Yeah, that point. Just looking ahead. Now a little recap. Airy function, everyone knows it is. It has one asymptotics. On one end, it has oscillatory asymptotics, some combination of the cosine with appropriate phase, and there are 2 solutions. Throw in a physical solution could not be exponentially growing. Exponential decaying is the well-known Airy function, right? So to connect, if you start from the right end, as John told us, to go right to left, you have exponential growth, right, in the opposite direction. And which of the a priori you can guess that there will be 2 combinations of that. There will be a particular mixture of the 2, but you need to do something else to detect the coefficients of the mixture, right? And you need to know method of steepest descent, for example. So, of course, even here already, that's my already first hope to qualify for this workshop. It's already exponentially small phenomena happen here. Since Airy function decays, if I go a little further inside the domain, further away from the boundary, the solution quite quickly becomes exponentially small. Essentially, this supports the intuition, right? I need to take one of the roots, right, of this red function to take a nail, right, and put the boundary, how I visualize it, the boundary condition. There will be a few oscillations inside the domain and then exponential decay. So it's consistent with that intuition, what we hear in St. Paul Cathedral or elsewhere, as John reminded to us. Now, we will also know that it's kind of, it could be done fully, like still talking about classical concave boundaries. Yeah, it's kind of a main order term can be guessed from usual stretching, but then you can systematize it into all orders asymptotic expansion for with Polingarity wave, and there is some easy kind of recurrent structure, the expansion in inverse powers of a large parameter k times 1/3, and this guy, the main order term is just classical area. The higher order terms are combinations of area and its derivative, and some prefactors, which are polynomials of growing degree. And that's kind of also rather routine procedure. What is behind it? You plug these ansatz into your equation, start differentiating. As soon as you can see a second derivative of Airy, you immediately replace it by eliminate it, right, from the Airy ODEs, and this seems to be a closed structure. And then you watch for this prefactor, there will be simple recurrent relations. So they grow like as a polynomials. The one step up, it goes what polynomials acquire extra power 2. Polynomials of n degrees 2m, 2m. So then this kind of remains as what is asymptotic expansion, right? It's a formal series where in each next term is smaller order than the previous one, right? So if so each next term has extra 1/3 of k, and the polynomial degree is squarely, right? So you can argue that the domain of validity of this as classical whispering gallery expansion is up to k minus half, right? So between -1/3 and -1/2, solutions are already exponential small and still valid as asymptotic expansions, you can argue. Cool. Now, Popov asked out of curiosity, I suppose, I'm not sure he realized that it was a fundamental problem. I think over the years still, I think occasionally I meet people from different walks of mathematical life who in their own languages, in one way or other, arrived to this problem, and then they gave up because so if anyone has any ideas in the next 45 years how to advance it, you're welcome. So what is the mathematical problem here? This is a kind of intuition, right? If this is a physical thing. We have a whispering gallery going from the concave part of the boundary, but it approaches the inflection point. So what we would expect, that if I kept naively drawing this kind of small angle reflections, earlier or later this angle sheds off and never comes back to the boundary, right? There will be some kind of bunch of rays somewhere close to this limit ray, right, which I draw tangent from the inflection point. There will be some kind of concentrated beam. That's what the intuition suggests. And people call it a searchlight. A searchlight beam, right? So this publications probably was delay or lost in translation, right? How to there is in Russian the searchlight is called projector. Some Russian speakers here, right? Project. So if I ask my former compatriots how to translate projector, right? It's wrong. It's the wrong mathematical association. A searchlight. If you look at those papers, they put it out. When you see a projector, read it as a searchlight. That is what you should expect. So, and then if you are from here, the solution to the left, right, is considered near the boundary. If you go a little bit away, here it is exponentially small. But if you go round, and then it will be made systematic and more systematic in that paper, then it gives you an exponentially small, but then it starts surging somehow, shooting up on approaching this searchlight direction. That's the expectation, and that's what we will see. Now, how to formulate it is a mathematical problem. So just a boundary layer method again. You take a magnifying glass, right, a microscope. You look into the small neighborhood of the inflection point, and you have pretty good idea what is coming from the left to that. And then you need to get stretching. And again, if you rewrite, you need to take into account the curvature degenerates. Suppose it's kind of a first order inflection, right? A locally cubic boundary. Then it's kind of, if you do this, this is what Popov did, in fact, that time, then you can get that quite subtle. You need to do stretching along the normal as before, but with a different exponent, 3/5 rather than 2/3, right? And then you need to do additional stretching in the in the direction along the boundary, right, of the arc length S with k 1/3 power. It's also, if you think about it, it makes sense because it's local phenomenon localized in both directions. So, and after you do it, then you have, and it's natural also to take out this oscillatory thing, exponential as before, and everything else is encoded in this function of these two stretch variables, right? Call the first variable x, by analogy with, to be seen with Schrödinger equation, and this the other is t, right? X and t is already mentioned here, but no time here. This may be slightly misleading, but it will behave like, because it's kind of for the underlying reasons of causality or something in wave propagation, this will look a bit like time. In this stretched variable, this function solves this PDE, but it is there is a boundary. It is x is a stretched normal, right? Therefore, x is restricted to positive half line, and there is a boundary condition at x equal 0, and there is a prescribed asymptotics at the left end, inherited by the incoming whispering gallery wave. So you can do appropriate kind of usual procedure in matching, right, of outer and inner expansions. What is inherited from the outer when rewritten in the inner variables is some kind of Airy function, not surprised, and some exponential, not surprised either, right, since these two guys enter to whispering gallery ansatz, but with some quite sophisticated arguments, fractional powers of t, but this is asymptotic at minus infinity, right? And this is a well-posed problem, and then this is the big question, right? The mega, what happens at the, knowing this, a solution has a prescribed asymptotic behavior at large negative t, what is the asymptotic behavior at the other end? And if you can look at that, you can stare at this problem. Actually, forget about this half thing, right? Let's I u t, right, equals minus u x x. I just drop this half. You can scale it out. Minus x t u, and u and x is positive, right? First, and u of when x is 0, we have a Dirichlet condition. Very simple. That's all, right? Almost as simple formulation as of Fermat's last theorem, except the latter is soft, but this is still unsolved, right? So that's not sure which is harder, to be honest. But compare this with what? Does it look really similar to that, right? The area ODE, not much, but until you start looking at the more fundamental level. So about this guy, how can I guess that it has oscillatory behavior at one end, and forgetting about exponential, then we need to connect, right? Those two guys. An undergraduate student, so if I don't know anything, don't know WKB method, don't know. If I take x large negative minus million, right? Fix it, then I know that minus and minus plus sine and cosine are like oscillatory exponentials here. If I take x large positive, I have similarly exponentially growing, non-physical exponential decaying left. How to connect these two guys? I need to go step up in my undergraduate studies. I need to learn, for example, asymptotic methods, right? There is integral representation for the solution, steepest descents, and so knowing that here there is only exponentially decaying contribution, there will be a business, and that's a language you know better than me, right? Language of exponential asymptotics is one way of making sense of all this. So you can go around across Stokes and anti-Stokes line, account for them carefully on the complex plane, and connect minus infinity to plus infinity, right? you can start seeing the similarity, right? Here is instead the ODE, and if now I'm almost a postgraduate student, and I've learned PDEs and I've learned separation of variables, and instead of this guy, I have this guy T, and if I freeze it naively for minus billion, then I have a separable. This is negative, negative, it becomes kind of positive, right? And this has a separable solutions. What are they? I nu T times area of x minus nu. And then you have to satisfy the boundary condition. You have to discretize, right? So you can guess that here, it's my naive. So what is the analogy here? I need to draw not one axis, but two x, and x is positive, right? Here you have some kind of area type solutions, discrete. But here, similarly, if I equally naively froze x positive, I could have a guess what happens here, right? And there will be solutions with continuous rather than discrete nature, right? This new, you have to take a linear combination of two solutions. Actually, both will be oscillatory. There is no reason to eliminate either of them. Some linear combination of them would suffice. And both of those problems, incidentally, have kind of asymptotically discrete problem is actually just back to whispering gallery model. This asymptotically continuous is, those who know this is related to grazing diffraction, right? So there will be some combination. If I chose T as a large positive, scaled it out, there will be what's called Fokler-Antovich solutions. How to connect, and there will be not coefficients, but the whole integrals, right, over this parameter nu, right? And a gap in between. How to connect? No one knows through this, but there are some ideas we could prove it, make some advances, and maybe some numerics in a combination with that. So that's a problem. Okay, now I think I've said it all, right? This is analogy with asymptotics for area, right? X, and so you need. This is what all you need to know after all, right? The two you can interpret if it's in context of caustics. One would correspond to incoming part, the sound going, and the two are mixed with a phase shift, right? And that's the outcome of that asymptotic analysis of the integral. And as I think I've said this as well, right? That if you similarly freeze one guy to the other, then you can have seen that you have asymptotically kind of discrete modal or whispering gallery type behavior continuous at the other end. So this is the philosophic point, right? Selling point. This arguably as fundamental problem for connecting these two walls as a fundamental PDE, as Airy PDE is fundamental for connecting transitions from oscillatory to exponentially decaying here. So as I said, if you stare at this equation alone, you forget about whispering gallery. It's kind of becomes a mathematical problem, so problem of asymptotic analysis, if you like, right? Forget about this whispering gallery, but what can you say? It looks very simple, right? 1.5 line formulation, how to connect the things. But something is missing, still may be missing, yeah, for understanding it. So now, if I didn't know where it came from, would I be able to recover this asymptotic at the left end? Yeah, can I make this naive intuition of, you know, undergraduate student of the freezing T from minus million a bit more precise? Yes, I could. So if it were, and this is what is behind Popov's transformation, that if T was a large negative, I would just scale it out by this transformation. Instead of x, I take a cubic root of that, right? And then it splits equally between this new variable psi and x, right? But since T is not constant, there will be some kind of other garbage coming out. You need to rescale time by tau. They introduce some prefact, and as a result of this set, this is this naive intuition made working, but then there is a perturbation. Tau is a large parameter at infinity, and you recover in an honest way without knowing that there is an incoming whispering wave, that there will be, ignoring the perturbation, there will be a separable, asymptotically separable solution for corresponding to incoming whispering wave, but then there is a perturbation, right? And this allows you also to, in analogy, and this is what Popov did that time as well. This allows you to construct all orders, all order asymptotic expansions for this. Now we fully concentrate on this internal, like inner problem for the Schrödinger time PDE, right? For those I gathered this morning, that there is audience here, maybe more advanced than me in average, in dealing with kind of Schrödingers, but this looks like not classical Schrödinger. It is linear, but the potential is linear PDE, but with a linear potential, and it is linear, triple linear, right? Linear in x and t, right? But you see, for this reason, it's kind of analogy, right? Freezing t negative, you have area with one side. Freezing t positive, you have area with the other side, but t itself is linearly changing from one infinity to the other. What happens to that? It's very simple PDE, right? So if you have any ideas in the next 45 years, how to to make a PDE and boundary condition, half line, yeah, that's important. I would be interested to hear. So now you can make this similar all orders expansion. There is now in this. This also explains why these funny powers come from, right? Psi is rescaled x with this fractional power of negative t. Tau is also a kind of rescaled t, and then you have your asymptotics at the left end, right? Whispering gallery, all orders expansion, all orders expansion. Now, and again, you can see it's actually similar to that all order whispering gallery, that if when it remains asymptotic, so each next term acquires extra power of tau, which is t pi minus two-thirds, right? And extra square, like polynomials grow, right? Twice. We do simple calculations, so x could be anything from 0 up to 2 minus thirds, and since it is outside the exponent, so this guy psi may be quite big, and you're already in the domain of exponentially decaying solutions. So the wave field is already exponentially small, but this is still an asymptotic expansion in this sense, right? So it's actually summarized here. You need to be careful. There will be two significant terms because of this shift in the argument of Airy 3/2, as usual. This next order term, everything, there will be prefactor, everything else can be absorbed. You can construct full expansion here as well. So this is what I said, right? In this, in between minus third and plus half, right? It is both remains asymptotics and already exponentially small. So now, so this many years later, this tribute to Professor Babbage on occasion of his 90th birthday was a couple years ago now. At that time, I must admit, I was a postgraduate student, just there was no advanced computers, so I did some routine calculations, not really understanding, to be honest, the underlying ideas. And I start gradually appreciating ideas which Babbage had at that time. So now my current understanding, maybe it is still some way to go to improve my understanding. So he said, okay, let's try and do in this domain, right? We have this asymptotics of a whispering gallery somewhere here, far away. We don't know what happens here. We still have some kind of a some kind of a guess. In fact, this is transformed coordinates. In fact, this I need to look. That's already here one more time. Something should happen. Maybe better to visualize it on this more physical domains. There will be some kind of domain of validity of whispering galleries, incoming whispering galleries on the left, right? Which includes already, which remains an asymptotic expansion when the field is already exponentially small. There will be something here in this searchlight area. We are still not sure about, but can we try and go around along asymptotics in this stretched coordinates? It would correspond to try to do something analogous to connecting going on the complex plane in the area function, right? From minus infinity to plus infinity, and seeing if there are any Stokes type line and anything, and how to account for them and end up with correct answer at the other end. That was Babbage's idea in my current understanding. So I need to do what we need to do for that. We need to look at that equation, and now we need asymptotics on the left end. We re-expanded. We hope to find another exponentially small asymptotics here, which will match in some overlapping domain with the Springarian wave, and then see how far we can extend it. Maybe we can extend it up to this anticipated searchlight. So the series remains asymptotics, and then yes, I've said this already. Need to go further, right? Yes, that was essentially the outcome of that paper. I checked yesterday, day before. It's now available, I think, unrestricted. If you go for this Google Scholar and the link, it kind of gives you PDF unrestricted for those interested. I think there are some kind of ideas there which the mankind is still, myself including, the second co-author, still to fully understand and appreciate. Yeah, and maybe that they can make some further, who knows, advance in this big, still largely open problem, fundamental, as I argued at length, right? For all those reasons. So what we expect, there is a solution here which is exponentially small, and kind of the main order term is decaying exponentials, right? What would be a natural thing to do would be to try and find solution in forms of asymptotic expansions with put everything in the exponential, expect that S will be complex valued, right? So then I plug here, of course, I have something like this, right? Natural thing, there will be nonlinear equation, there will be second order term, but then if I expect asymptotics for large x and t, right, then I need to, usually, I need to, if I already put myself inside, I want to go a little bit outside, not stretched variable. What is the opposite of stretch? My poor English, shrunk variables, right? Like extend them a little bit. Then you introduce this unknown alpha, beta for x and t, right? Stretched. First I stretch them, then I want to go out, right, and get somewhere in the intermediate domain. All on that. And I need to do the same with this phase factor S, gamma. And then if I want to balance first three terms, there is only one choice available, right? Alpha is 3, beta equals 1, gamma equals 5. And then this guy will be of smaller order, right? Could be put on the right-hand side, ignored in the first place. And this is morally equivalent to doing seeking this ansatz exponentially small field, right? And that's in this form, right? And then you plug it as three terms like this. Just what is the difference between this cross and this new thing? The last term disappeared. It goes to the next order expansion. Incidentally, for full expansion, like all order expansion again can be built, constructed. Here, just small letters have been replaced by capitals, S, T, and X. But this is what nonlinear first order. Okay, it's kind of analog of a canonical equation, right? So, question to the audience, what will you do with that? I would, of course, start writing these equations for characteristics, then think that I need to complexify them. But, of course, Babbage said, forget it, this many years ago. First observation is two pieces of, and then this guy, that's here repeated, this is this aconal type equation, but with expected complexity is S, right? Must have mixed. I sort of if there were no exponential decay, right, in it, everything would have been real valued, right? But because this guy is already exponentially decaying, S itself should be decaying, so asymptotically. But this guy actually has some hidden self-similarity in it, not immediately obvious. So again, it's invariant under this change of back with the same factors. Maybe it's not surprising, this epsilon replaced by alpha, right? The same factors, cubic, minus, and 5. This means that it has a particular solutions, essentially reducing ODE to PDE, right? Other way around. PDE is reducible to ODE. So it is a self-similar or quasi-homogeneous, I think it is called, right? If, it could be written as a t to the power 5 function f of a single argument, x over t cubed. And then this guy transforms to PDE, transforms to ODE, right? Okay, next question to the audience. What do you do with this ODE? So Babish again knows how he knows all that. How can you? Still knows. I suppose this actually is a explicitly solvable ODE. Who would believe it? Even for allowing for it is actually a D'Alembert, sometimes called Lagrange D'Alembert ODE. So is it? I should refresh my. Is it first or second year undergraduate curriculum? So if you have unknown function, is a linear combination of a function of unknown function times the variable plus another function of unknown. Yeah, this is by you put f prime as a new variable, call it p, right, and differentiate, and then you reduce it to integrable first order linear ODE, right, by some clever tricks, and you have the solution in a parametric form for this equation. So there is some a parameter, a constant of integration c, and there is yeah, essentially, and there is a choice of if you want to eventually to have f as a function of lambda, right? You need to solve a cubic equation, right? You have roots of that, and one root will be one root will always, at least one root will be real, right? For this c of lambda, right? Actually, some change of variables makes it in a more canonical form, right? So f, not surprising, I suppose, maybe still looks a bit of a magic to me that so f has some kind of constant linear and quadratic functions all identically 0. Here it's also kind of, this is a canonical form of that thing, and this is what happens. You need to inverse it, and you, only one choice, and you go to this negative, so lambda, what is lambda? Oops. Lambda is x over, yes, x over t cubed, right? This kind of this thing. So if you are here, you want to go there. That's just, it has to be negative first because t is negative and it is small negative, right? So if lambda, and you have prescribed asymptotic behavior for negative lambda, but it is complex, and you for this you plot this cubic. Something I was well qualified that time as a PhD student of Babbage. You're enough qualified enough, not sure about more advanced stuff. Cubic equation, it has, depending on lambda, you'll have either all three roots, reals, or one real and two complex values. And since you go to small negative things, you need to choose, forget about real, or choose appropriate complex valued root. And then you go along that, essentially this, and then you go to infinity, but infinity is a regularizable thing, right? So you have this psi is a complex variable. This has a real part and imaginary part. You go from 0 down there and then go happily through infinity. You can make it systematic. Look at that paper which does it. And then you return back to this other thing. And then it breaks up right here. So this is exponentially. So that's exactly what happens. It is you match, you do a perfect match it here in all orders. You go exponentially small, it remains exponentially small, and then it starts surging when you approach this suspected searchlight. So that's already something, right? And this is Babbage. In that paper, we did this calculation. This is kind of boundary layer method. It has some routine elements where I felt that I could do the turn in the handle routinely at that time. one of few things, I was qualified enough. So, and then you do this calculation, essentially, you see how this the searchlight, this exponentially small field starts surging, ceases to be exponentially small, and then you start watching where up to which point it keeps asymptotic nature, right? It remains asymptotic expansion up to this, and you have this from this other peak. Lambda equals 1/6 corresponds to what this cubic parabola x equals 1/6 t cube. And this is exactly, it is exactly the limit ray, right? So somewhere here it starts surging and breaking up, but it also suggests also the ansatz for the searchlight, right? Since you look, you see where it, the shadow for re-expansion of the in the form, right? So, so it has this form, and when this eta becomes as it breaks it breaks up of in what does it say in it's here. Full expansion is constructed on this way, matching whispering gallery and valid for here, and then then it remains valid as long as you don't come too close to this to the limit ray, essentially, written in this curvilinear stretched curvilinear coordinates, right? And this also suggests for you it surges, right? For start shooting up, growing exponentially, but from exponentially small background. So loses asymptotic character. But it also suggests the scaling for this another boundary layer in the neighborhood of the suspected searchlight. And if you do this an anticipated matching, right? You do this rescaling, there is this kind of natural kind of, you see, yes, eta, right, is a rescaled variable. T is now large positive parameter. And then you have another asymptotic series for some asymptotic series for eta going to plus infinity, right? This is your anticipated ansatz for the searchlight. Now, then we did, it's also in that paper, which has far-reaching implications. I realized this many years later, that if this kind of, what remains is a kind of a regular expansion, right, in inverse power. So this is the only unknown remaining here. But if you denote this whole thing by G and rewrite this equation, this Popov's equation in this variable, it looks precise, suspiciously simple PDE, right? We were puzzled about it that many years ago, ignored it, but it was actually not a good news because it didn't really provide a clue for matching, and there were physical reasons for that. You could not really, if you could do this unless you do something, maybe the audience will have some ideas here if you do some more subtle account of whatever, some analogs of Stokes lines or whatever there could be in a brute force way. Well, because T is a large parameter, right? Then what? Like this is main order term G naught. Take it arbitrary, but the only condition has to have all the prescribed asymptotics at plus infinity now, right? I look up in these new things, and yeah, of course I can take it rather arbitrarily, but then the recurrence relations are what this is. When many years later Ilya Kamotsky joined me, he said, look, first, why don't you do this simple change of variables? Tau is inverse T, right? Then of course it becomes Schrödinger equation without potential, right? First. Second, that's not a surprise. Could have been guessed because essentially this means that Popov's PDE by some mysterious transformation is reducible in this. Just a lot of things, but you reverse time, you put some funny prefactor here and something else, and this new function and new variables solves suspiciously simple PDE, right? Free Schrödinger. But that's exactly, that's related to what is some people call a pseudo-conformal symmetry of free Schrödinger equation. So actually these names appeared earlier this morning in remark from the audience. And this is what Ilya Kamotsky, my co-author, precisely he dug this reference, Talanov, 1970, and two Sulims were mentioned. They may have. I think that's not a coincidence. I'm to understand better the relation. But we found it famous Terry Tower, right, who writes some insightful online notes, right, not bothering publishing papers, right, for the real-life classics. In one of his online notes, we actually referred to that in our paper, of this year paper, that this is a simple change of variables in a free Schrödinger equation in the complex conjugate to leave plus sign by the plus sign. And that's in turn related to the view on the inflection problem of John Ockendon and Richard Yu, who said, forget about curvilinear coordinate, do stretchings directly in Cartesian coordinates, right? Then you have this from the very big, you don't have this linear potential, but of course no free lunch, you have a curved boundary, right? So as soon as you forget about boundary, then this guy translates to this guy by this explicit, quite simple invariance transformation. For us, it was useful to make with Ilya, right? Now, 36 years later, right? Like in a movie, right? First part, the second part. Now, 36 years later in this paper with Ilya, this was correct guess, right? But we didn't know what to do with that time. We still don't know, except that Ilya is more kind of analysis type guy than myself. But we can prove a theorem that this is precisely. We still have no clue what the searchlight amplitude is, but it somewhere exists in nature. How to capture it's a different question, right? If there exists some well-defined function with certain properties, you can prove it as a theorem, and you can say precisely that exact solution at the other end must have this searchlight asymptotics in terms of still unknown, except for its some qualitative properties, the searchlight amplitude. Maybe I'll skip this for this is kind of the precise result, and there's some ideas how to make them work, and they're based on this asymptotic expansion, extension, and truncation, and carefully controlling the error. Whichever language you speak, right? Okay, and that's essentially the open question. Now, I run out of time, I believe. Yeah. So, except you could try and do it either. You can hope that you can do some numerics, supplement this way, because it's still how to compute this asymptotic, so searchlight amplitude, essentially G naught of eta, right? All you need to know, but maybe more if you want to go further down to the boundary and match it to you expect some what is called creeping waves. Yeah, you even had a problem. No one knows really, right? And that's of course I ran out of time. So one possibility would be to reduce it to an integral equation, to invoke some kind of numerics, but hopefully also integral equations allow to do some further asymptotic analysis to make more precise statements. There are some kind of developments here, just to flash in front of you. But maybe since I announced this anyway, no time for that. This is now my kind of part from the other side of the former Iron Curtain, in a Science Journal, 2007, exponential, what we call exponential homogenization, which it's kind of, here was just a routine calculation, and my curious thing that just to flash in front of you. So people know that if homogenization, right, you have a PDE with rapidly oscillating coefficients, right, a periodic in simplest case, periodic with a period epsilon, right? This means that you have some underlying coefficient, period 1, but you rescale period epsilon as here. Now you want some not only all orders, but hopefully beyond all order expansion, better to avoid boundary layers, because boundary layers and homogenization is a nightmare, another big open problem, right? A way to cheat is just to have some kind of fixed periodicity, right? Some technical thing, look at that paper, and then you have to discretize epsilon, right? To be a small parameter. Then people knew it before. You have all order expansion, all order two-scale expansion homogenization. It has this structure, and it has separation of fast and slow variables in all orders, right? And then you have usual kind of, you can prove theorems. But if you do, that's the last slide. If you do truncation, right? If you do truncation, if the right-hand side is nice, analytic, optimal truncation, or a number of terms itself is of order epsilon inverse, then you can prove that the error thereby committed is inappropriate norm, L2 in this simplest case, is exponentially small. That's it. And this is my summary, and this is a question to the audience, right? Inflection problem, really a tough one. Forget about Riemann hypothesis, right? It's Fermat large theorem is already proven, not interest. So what can, very simple, right? PDF. So, and there are some indications, including from my current vision of that PhD work with Babbage of many years ago. There was some ideas of buried behind that calculation and that matching business. Can exponential symbolics and inference helps to connect the two ends. Thank you very much.
So I think rather than take the questions, we might want to get some coffee first.
Yeah.
But there's two discussion sessions this afternoon, both in seminar room 1 and seminar room 2. And so I would encourage you to go talk to Valery about some of these open challenges. And also you can tell us more about the homogenization later in the week as well.
Yeah.
All right, thank you. Let's thank him again. And then there's, just to remind you, there's, so the discussions will go on to 5 p.m. There's no plan for the discussions. You can mill about in the 2 seminar rooms, seminar room 1 and 2. And then we'll see you all for the wine reception at 5 p.m. that runs from 5 to 6.
So I'll dispose of this.
Sorry, I had to.
Yeah, sorry, yeah.
What are you sorry about? What are you sorry about?